Hello everyone, my name is Pranav Teja. I welcome you all to my PPT presentation. Let me introduce myself. My name is N. Pranav Teja. My roll number is 2195186688. I am from CSM branch, IARA College. The subject is Basic Electrical Engineering. This presentation is going to be on the subject Basic Electrical Engineering, and the topic I will be discussing in this next slide. So I hope you will enjoy my PPT presentation. Uh, Without further waiting, let's get started. So my topic is laws of magnetism. So what is magnetism? What are its types, and what are the equations which are involved in it? How does it function? What are its uses? Let's discuss. I'm going to discuss the laws of magnetism on I would like to view the general idea of what magnetism looks like. I'm not going to depth of these topics. uh, this is a very interesting book. You can buy and solve problems on magnetism, which is very interesting. This book is, if you solve this book, you will become expert in solving any electromagnetic magnetism problems. This is actually for, you can use this if you solve this book, you can easily crack IIT, any IIT college. If you in physics, this book is called IE Rodo. These books are very awesome. So without without waiting, let's get started. So, four laws of magnetism. The operation of electric motors is governed by various laws of electricity and magnetism, including Faraday's law of induction, Ampere's circuital law, Lenz's law, and the Lorentz force. The first two, Faraday's law and Ampere's circuital law, are included in Maxwell equations. Together with Lenz's law and the Lorentz force, these principles form the basis of electromagnetism. Um, Faraday's laws of induction. Faraday's laws of induction is the fundamental law on which electric motors operate. Michael Faraday is credited with discovering induction in 1831, but James Clerk Maxwell described it mathematically and used it as the foundation of his quantitative electromagnetic theory in the 1890s. So there are four laws in electromagnetism that we will be discussing, and the four equations, the main four equations that we have to keep in our mind are, those equations are called as Maxwell's equation, Maxwell equations. The first one is Faraday's laws of induction. The first one that we are going to discuss is Faraday's laws of induction. He, what this guy Faraday found out that by using magnetic, we can induce electric current. The electrons can flow by movement of magnet in movement of a conductor in a magnetic field. If you place in magnetic field, the current is induced. Inductance is a property of a device that tells how effectively it induces an EMF in another device or on itself. Faraday's law generally states that in a closed coil loop of wire, a change in the magnetic environment of the coil causes a voltage or EMF, electromotive force, to be induced in the coil. The change in magnetic environment can be caused by changing the magnetic field strength, moving the magnet toward or away from the coil, moving the coil into or out of the magnetic field, or rotating the coil in the field. The induced EMF equals the negative rate of change of magnetic flux times the number of turns in the coil. See, what is magnetic laws of induction states that is, in a magnetic field, if we no, in a, states that in a closed loop of wires like this object over here, if we place the magnet inside this coil, or wherever these coiled foils are, if we place inside and move it forward towards and away from the coil, he Faraday found is that he found that deflection in this meter, in this ammeter. So he discovered that by using a magnet we can produce electricity. So he found out that that gave that actually is the power. It is that actual, from that idea that he uh, found out Faraday's law. So he found out that with magnet also, with magnet we can actually make electricity. If we move magnet, if we rapid movement, if we do to a magnet in a field of coils, in a loop, we can actually see a current flowing through it. So the induced EMF E is equals to minus N delta phi by delta T, where E is equals to EMF, the EMF generated. N is equals to number of turns in the coil. The more number of turns in the coil, the more EMF is generated. The more EMF is directly proportional to number of coils. So the phi is equals to magnetic flux, Weber WB. The phi is the magnetic flux, or the strength of the flux that it is producing. More the number of more the EMF produced, EMF is proportional to magnetic flux. T is equals to time. How with respect to time, how rapid the movement is taking place, uh, how fast the magnetic is moving toward and away from the loop. Note that magnetic flux is equal to the average magnetic field B Tesla or Weber per meter square multiplied by the perpendicular area of the coil that penetrates the magnetic field A meter square. So the magnetic flux is equals to the average magnetic field B. Magnetic flux is also related to the magnetic field. More the magnetic field, more the magnetic flux is generated. B multiplied by the perpendicular area of the foil that penetrates the magnetic field. Now let's look at the second law of electromagnetism. The first was Faraday's law of induction. Second law is that Lenz's law. Lenz's law demonstrates the reason for the negative sign in Faraday's law of induction. In other words, Lenz's law explains why the EMF generated according to Faraday's law is negative. A common way to state Lenz's law is when EMF is generated by a change in magnetic flux, the polarity of induced EMF is such that it generates a current whose magnetic field is in a direction that opposes the change that produces it, the original magnetic field. That is, induced magnetic field always works to keep the magnetic flux constant. So we have to understand, what we have to understand is, let us look at it closely. So what Lenz's law means is, when EMF is generated by a change in magnetic flux, the polarity of the induced EMF is such that it generates a current whose magnetic field is in direction that opposes the change that produced it. So a change in magnetic flux is produced. Hmm? The polarity of the induced EMF is such that it generates a current whose magnetic field is in a direction that opposes the change that produced it. Wherever that the direction of magnetic field is passing, the EMF tries to oppose that magnetic field so that it remains constant. That is, the induced EM magnetic field always works to keep the magnetic flux constant. So here is the diagram that illustrates the Lenz's law perfectly. Here in this first diagram, the magnetic here is placed near this loop, and it is going towards it, and flux is being induced, and it is, if it is away from this loop, it is uh, so this is the way this Lenz's law states. This is the actually tries to uh, make electric flux, magnetic flux constant. When the magnetic flux changes delta B, the magnetic field of the induced EMF B induced works to counter the change. It doesn't want the magnetic flux to change. It always keeps it constant. That's why this Lenz's law is famous. Lenz's law is analogous to Newton's third law in mechanics, which states that for every action there is an equal and opposite reaction. So it is actually kind of similar to Newton's third law, that if you try to change something, it doesn't want to change. It has a natural tendency to it has its own reaction that makes it constant. The previous Lenz's law is actually kind of same to that yeah, if you try to change the magnetic flux, it doesn't change. It will try to keep the magnetic flux constant. The induced EMF tries to keep the magnetic flux constant always. Lorentz. Now let us look at the third law of electromagnetism, that is Lorentz force. This is a disagreement over whether the Lorentz force was originally derived by James Clerk Maxwell or by Oliver Heaviside, but credit is typically given to Heaviside. Hendrik Lorentz derived the modern form of the equation in 1891. The Lorentz force is the force that a particle experiences due to electric and magnetic fields. Electric fields exert a force on a particle whether it is moving or not, while magnetic fields exert a force only when the particle is in motion. The combination of forces from electric and magnetic fields is given by F is equal to Q bracket E plus VB, which simplifies to F is equal to QE plus QVB, where F is equal to force, Q is equal to particle of charge, E is equal to electric field, V is equal to velocity perpendicular to magnetic field, B is equal to magnetic field Tesla. This is the equation of Lorentz force. Uh, this is F is equal to force, Q is equal to particle of charge, E is equal to electric field, V is equal to velocity perpendicular to magnetic field, B is equal to magnetic field Tesla. Since current is essentially a stream of moving charged particles, it also experiences force due to magnetic field. In the case of a current in a magnetic field, the Lorentz force equations becomes F is equal to L times L cross B, where L is equal to current, uh, where I the equation I am repeating this equation, F is equal to I into L cross B, where L is equal to, I is equal to current and L is equal to length of wire through the field. The direction of the Lorentz force is derived using the right hand rule. Point your thumb in the direction of your first finger in the direction of the magnetic field, and your second middle finger will point in the direction of the force. So by using right hand rule, we can we the direction of magnetic field, the direction of force and current is we can tell. Now fourth law of electromagnetism is Ampere's circuit law, which is important. Despite its name, Ampere's circuit law was derived not by Henri Marie Ampere but by James Clerk Maxwell in 1860s, and is one of the Maxwell equations of electromagnetism. Ampere formulated Ampere's force law, which describes the attractive or repulsive force between two current carrying wires. The magnetic field exerts a force on a straight wire that is carrying current. With Ampere's circular law, the strength of the magnetic field can be determined by B is equal to mu naught I by 2 pi r, where B is equal to magnetic field T, mu naught is equal to magnetic permeability of air T, 1 by A, I is equals to current A, R is equals to distance from the wire M. When the wire is a loop, the magnetic field causes a force in one direction on one side of the loop and in the opposite direction on the other side of the loop. This creates a torque which causes the coil to spin. Note that if direct current is applied, the coil will oscillate back and forth but will not make complete revolution. This is the reason DC motors use commutators. Motors that are operated with alternating current AC motors don't exhibit this problem. Derivation of Ampere's law. See, this is the image that derives the Ampere's circuital law. This is from Biot-Savart's law. The magnetic field due to a long straight wire is B is equal to mu naught I by 2 pi r. Since B and DL are in same directions, B dot DL is equal to B DL cos 0 is equal to B DL. A is equals to electric current, B is equals to magnetic field, mu naught is equals to permeability of free space. Therefore, B dot dl is equals to mu naught I by 2 pi r into integration of dl. B, this equation is finally derived to uh, this is the integration of B dot dl is equals to mu naught I. The current inside, the summation of current inside into the summation of current inside into magnetic field is equal to mu naught I. This is the Ampere's circuital law. Now let us sum up the four electromagnetism laws that we have discussed in the previous slides. These are the Maxwell equation of electromagnetism. If you remember these four equations, these are the general equations. From these, every other concept in these particular topics are extended from these equations. These are important ones. Without these, no further no problems can be solved in electromagnetism topic. Maxwell laws of electromagnetism. Gauss law for electrostatics. E dot dA is equals to Q by epsilon naught. Gauss's law for magnetism. B dot dA is equals to 0. Faraday's law of induction. E dot dl is equals to minus d phi p by dt. Ampere's law. And B dot dl is equals to mu naught I plus mu naught epsilon naught d phi e by dt. Thank you. I hope you enjoyed my PPT. Thank you everyone.